In a previous lecture, we worked through the formal definition for several types of limit. All of them were challenging to apply to specific situations. To prove that the limit of an equals L for a given sequence an, we had to find a formula for a number cap n sub epsilon such that if little n exceeds cap n sub epsilon, then the absolute value of an minus L is less than epsilon. For a limit involving a function at a point, the limit as x tends to a of f of x equals capital L. It was even more complicated since we had to provide a formula for determining a function delta of epsilon so that absolute value of x minus a positive and less than delta implies absolute value of f of x minus L less than epsilon. It's easy enough to use these definitions to show that the limit as n tends to infinity of 1 over n is 0, or that the limit as x tends to a of x is a, but there are uncountably many other sequences and functions to deal with. We really don't want to go through this entire process again if we want to show, for example, that the limit of n divided by 2n plus 1 is a half, or that the limit as x tends to a of x squared minus 3 is a squared minus 3. So we get smart and establish a list of theorems, usually referred to as the limit laws. To state these laws, we have to introduce an algebra for sequences and functions. Since sequences are just functions with domain the natural numbers, we could just give one version of each algebraic operation. But we're going to state the operation separately for sequences and functions because they have a different feel. If an and bn are two sequences, then their sum is the new sequence whose nth term is an plus bn. If f of x and g of x are two functions, their sum is a new function whose value at each point x is f of x plus g of x. For example, the sequence 2n plus 1 over n is the sum of two sequences, 2n and 1 over n. Similarly, the function 2x plus x squared is the sum of the functions 2x and x squared. Subtraction is defined analogously. Similarly, we can multiply a sequence or a function by a constant c to get a new sequence or function. If an is a sequence, then each term of the new sequence will be c times an. That is, multiply every single term by c. For a function f of x, the function c times f has the value c times f of x at each point x. For example, the sequence 3 over n can be thought of as 3 times the sequence 1 over n. Multiplication is next. If an and bn are two sequences, then their product is a new sequence whose nth term is an times bn. If f of x and g of x are two functions, their product is the new function whose value at each point x is f of x times g of x. For example, the sequence 1 over n times n plus 1 can be thought of as the product of two sequences, namely the sequence 1 over n and the sequence 1 over n plus 1. The function h of x equals x squared can be thought of as the product of the function f of x equals x with itself. H is f times f. Finally, division is defined in what by now should be the obvious way. If an and bn are two sequences, then their ratio is the new sequence whose nth term is an over bn. If f of x and g of x are two functions, then f over g is the new function whose value at each point x is f of x over g of x. For example, the sequence 2 divided by 1 plus 3 over n can be thought of as the ratio of the sequence which is constant at the value 2 divided by the sequence with the nth term 1 plus 3 over n. The function sine x over x squared can be thought of as the ratio f over g, where f of x is sine x and g of x is x squared. Now we can state the limit laws. Let an and bn be two sequences and assume that each converges to a limit. Lim an is equal to capital A, say, and the limit of bn is capital B. Let f of x and g of x be two functions and assume that each has a limit as x approaches a. The limit at a of f of x is L, and the limit at a of g of x is M. Then, the limit of a sum is the sum of the limits. The limit of an plus bn, the new sequence, is lim an plus lim bn, that is just a plus b. The limit as x tends to a of the new function f plus g is just the limit of f of x plus the limit of g of x, L plus m. Secondly, the limit of a product is the product of the limits. The limit of the sequence whose nth term is an times bn, that is the product of the two sequences an and bn, is the product of the separate limits, a times b. And the limit of the product of the two functions f and g is the product of their limits, L times m. Third law, if the denominator does not have limit 0, then the limit of a ratio is the ratio of the limits. That is, if b is different from 0, then the limit of the ratio an over bn is just a over b. If m is different from 0, that's the limit of g, then the limit as x tends to a of f over g is L over m. And finally, the last law, multiplication by a constant c multiplies the limit by c. That is, the limit as n tends to infinity of the sequence whose nth term is c times an is just c times the limit of the an. And the limit of c times f of x as x tends to a is just c times L. That is, c times the limit as x tends to a of f of x. These laws give us a powerful tool for building up a portfolio of known limits. For example, knowing that the limit as n tends to infinity of 1 over n is 0, we can immediately conclude that the limit as n tends to infinity of c over n for any constant c is equal to the product of two limits, namely the limit as n tends to infinity of the constant sequence c, every term in the sequence is c, multiplied by the limit as n tends to infinity of the sequence 1 over n. Well, the limit of the constant sequence as n tends to infinity is just the constant c, and the limit of 1 over n as n goes to infinity is 0. C times 0 is 0. So the limit of c over n is 0. Now we use the product law to look at the limit as n tends to infinity of the sequence c over n squared. That's a product of two sequences, c over n times 1 over n. Both of these sequences have limit 0, and the limit of their product is the product of their two limits, 0 times 0, which is 0. So we conclude that the limit as n tends to infinity of c over n squared is 0, and then you can conclude that the limit as n tends to infinity of c over n cubed is 0, because that's just the product of the two sequences c over n squared and 1 over n, both of which have limit 0. And then a simple induction proof shows that the limit as n tends to infinity over c over n to the p is 0 for any natural number p. Now we can use our divide numerator and denominator by something useful trick to determine more complicated limits. Let's look at the limit as n tends to infinity of the ratio of 2n squared plus 1 to n squared plus 2n plus 4. We look for the highest power of n that appears anywhere, and we see that that's n squared. And so we divide numerator and denominator by n squared. And this becomes the limit as n tends to infinity of 2 plus 1 over n squared in the numerator, and downstairs 1 plus 2 over n plus 4 over n squared. And now the limit of a ratio is the ratio of the limits. So we take the limit of the numerator, 2 plus 1 over n squared, if we can figure that out, and then we try to evaluate the limit of the denominator, 1 plus 2 over n plus 4 over n squared. Look at the numerator and use the sum law. The limit as n tends to infinity of 2 plus 1 over n squared is the limit of 2, the constant sequence, plus the limit of 1 over n squared. And that's just 2 plus 0, and that's 2. Now the denominator, and again use the sum law. The limit of 1 plus 2 over n plus 4 over n squared is the limit of 1 plus the limit of 2 over n plus the limit of 4 over n squared. And that's 1 plus 0 plus 0, and that's 1. So the limit of our original sequence is 2 over 1, which is 2. The same principles work for limits of functions, and we leave these to the posted notes for this course. The laws extend to limits at infinity for functions. Consider the limit as x goes to infinity of the ratio 2x squared plus 3x plus 1 divided by 3x to the fourth plus 2. We divide numerator and denominator by the largest power of x in the entire expression, which is x to the fourth. And that leaves us with the ratio of 2x to the minus 2 plus 3x to the minus 3 plus x to the minus 4 divided by 3 plus 2x to the minus 4. Now apply the quotient rule. Take the limit of the numerator and divide it by the limit of the denominator. As with sequences, it's easy to show that for any natural number p, the limit as x goes to infinity of x to the minus p is 0. So you can apply the sum law and the law for multiplication by a constant to the numerator and denominator. And for the numerator, you get a limit of 0. For the denominator, you get a limit of 3, and therefore, the limit of the original expression is 0 over 3, which is 0. Finally, we can also use the limit laws along with some common sense observations to evaluate limits when one or more of our functions blow up as x tends to a. Our techniques work with one-sided limits as well. One observation we can use is if the limit of g of x is plus infinity or minus infinity, that is, g blows up as x approaches a, or in other words, a is a vertical asymptote. And if the limit as x tends to a of f of x is some number b, then the limit of the ratio f of x over g of x must be 0. For example, consider the limit as x tends to pi over 2 from the left of x over tan x. Here is a graph of tan x to help. It is clear that the limit as x tends to pi over 2 from the left of tan x is plus infinity. And we know that the limit as x tends to pi over 2 from the left of x is just pi over 2. So the limit of the ratio is 0. Now that we have established the usefulness of the limit laws, we can consider the proofs. Detailed proofs we post elsewhere. In this lecture, I just want to focus on the fundamental ideas behind the proofs. A key tool that you need for all of these proofs is the triangle inequality. It states that if p and q are real numbers, then the absolute value of p plus q is less than or equal to absolute p plus absolute q. So let's look at the sum law for functions. We are given that the limit as x tends to a of f of x equals L, and the limit as x tends to a of g of x is m. This means I can keep the values of f close to L and simultaneously keep the values of g close to m by keeping x minus a small enough in absolute value. In mathematical terms, we are given that absolute f of x minus L and absolute g of x minus m can be made as small as you want by keeping x minus a sufficiently small. We want to show that we can keep the sum f of x plus g of x minus the sum L plus m in absolute value less than epsilon. by keeping x minus a in absolute value sufficiently small. We'll take that desired inequality and regroup the terms. Write f of x plus g of x minus the quantity L plus m as f of x minus L plus the quantity g of x minus m. Same expression, just regrouped. Put absolute value signs around it. And then think of f of x minus L as p and g of x minus m as q in the triangle inequality. So that absolute value is less than or equal to absolute value f of x minus L plus g of x minus m. And you need to make that less than epsilon. But that's exactly what you can do, because for x sufficiently close to a, you know that you can make f of x minus L arbitrarily small and g of x minus m arbitrarily small. And that's the core idea of that proof. For the product rule, we are given as usual that the absolute value of f of x minus L and the absolute value of g of x minus m can be made as small as you like by restricting absolute x minus a. But now you need to convince me that you can make the product f of x g of x minus L times m small by restricting x minus a. And all of these expressions have absolute values. So the trick is this. Write the absolute value of f of x times g of x minus L times m in a special way as the quantity f of x minus L times g of x plus the quantity g of x minus m times L. Just do the simple algebra and you'll see that's the same expression as before. But now you can use the triangle inequality on this new expression. And you get that f of x g of x minus Lm in absolute value, using this special way of writing it, is less than or equal to the quantity f of x minus L times g of x, absolute value, plus the quantity g of x minus m times L in absolute value. Now use the obvious fact that for any numbers p and q, the absolute value of the product is equal to the product of the absolute values. And you can write absolute value f of x g of x minus L times m is less than or equal to absolute value f of x minus L times absolute g of x plus absolute value g of x minus m times absolute value L. At this stage, we can use common sense to see the rest of the argument. G of x is close to its limit. So the term absolute value f of x minus L times absolute g of x can be made as small as you like by restricting absolute value x minus a. Since cap L is just a fixed number, you can make the second term absolute g of x minus m times absolute L as small as we like by restricting absolute x minus a. Since we can make each term small, we can make their sum small, and therefore we can make absolute f of x g of x minus L times m small. So to recap, we have presented and demonstrated the use of a set of simple laws for limits which allow us to evaluate the limit of complicated expressions by breaking it down. We can now use these laws as tools for evaluating the limits we will encounter in our development of the calculus.